Good day everyone. Today we will discuss about glycerol metabolism. Learning objectives. At the end of the lesson, the student should be able to describe, explain the process of tetraglycerol mobilization and identify its product including glycerol and fatty acid. Discuss how glycerol metabolism integrates with carbohydrate metabolism. Outline the two-step metabolic pathway of glycerol. Describe the role of enzymes such as glycerol kinase and glycerol 3-phosphate dehydrogenase in glycerol metabolism, emphasizing the use of ATP and NAD+ in reaction. What is glycerol? Glycerol is a colorless, odorless, viscous liquid known for its hygroscopic and humectant properties. It is a key component of lipids and plays a role in carbohydrate and lipid metabolism. So, glycerol is a clear, odorless liquid that attracts and retains moisture. It occurs naturally in fat and oils, and it's commonly used in products like lotion or food. Additionally, it plays a key role in metabolizing fats and carbohydrate in the body. Application in health and industry. Glycerol is widely used for cosmetics, pharmaceuticals, and food. The application includes skincare, as moisturizer, bowel health for laxative, and enhancing athletic performance for hydration. Glycerol's useful extends far beyond just being component of fats because it's a good at attracting holding water. It's a star ingredient in many cosmetic and personal care products as moisturizer. Glycerol is the most abundant in beauty products like lotion and moisturizer, creams, and etc. In pharmaceutical world, it helps dissolve medication and keep them stable. Even in food, it acts as humectant, keeping things moist and preventing dryness. Beyond this, glycerol can even aid bowel health as a laxative and improve hydration for athletes, so it's truly a versatile substance with application across many industries. Importance of glycerol in pharmaceuticals. Glycerol is essential in pharmaceuticals for its ability to dissolve drug, retains moisture, and lubricate formulations. It is used in various products including suppositories, capsules, tablets, and artificial membranes. It also has a medical application for constipation, pressure reduction, and for dissolving drug, retaining moisture, and lubricating formulation. It is commonly found in products like suppositories, capsules, and tablets, and used in medical treatments for constipation and pressure reduction. And overall, glycerol is most abundant in pharmaceuticals and also in our body because of the ability to hold moisture and overall.
Pathways of glycerol metabolism. Glycerol metabolism involves two primary pathways. They are gluconeogenesis and lipid synthesis. First is the gluconeogenesis. So, the chart shown depicts the metabolism of glycerol through these steps. First is glycerol uptake. Glycerol enters cells and undergoes phosphorylation with the enzyme glycerol kinase, forming glycerol 3-phosphate or G3P. Then, the oxidation of G3P. G3P is oxidized by glycerol 3-phosphate dehydrogenase, producing dihydroxyacetone phosphate or your DHAP. DHAP in metabolism. DHAP enters the glycolysis pathway to generate energy or participates in gluconeogenesis for glucose synthesis depending on cellular needs. So enzymes and intermediates are highlighted, showing how glycerol integrates into broader metabolic pathways. Next is lipid synthesis. So for lipid synthesis, the chart shown illustrates how glycerol contributes to triglyceride formation. First is glycerol conversion. Glycerol is phosphorylated by glycerol kinase, forming glycerol 3-phosphate. Then phosphatidic acid formation. G3P reacts with two molecules of fatty acyl-CoA via acyltransferases, creating phosphatidic acid. Then diacylglycerol production, or DAG. Phosphatidic acid is dephosphorylated by a phosphatase to produce DAG. And lastly, triglyceride synthesis. DAG combines with another fatty acyl-CoA via an acyltransferase to form triglycerides. So this pathway is important for energy storage and membrane lipid biosynthesis.
The metabolism of glycerol involves several key enzymes, each playing a crucial role in converting glycerol to intermediates in various metabolic pathways. And these are the following. First is the glycerol kinase. Glycerol kinase is the first enzyme in the glycerol metabolism pathway. This enzyme is responsible for phosphorylating glycerol to produce glycerol 3-phosphate, or the G3P, using the ATP or the adenosine triphosphate as a phosphate donor. Glycerol kinase is primarily localized in the liver, where it plays a significant role in gluconeogenesis. Next is the glycerol 3-phosphate dehydrogenase, and it is divided into two forms. The first form is the cytosolic. Cytosolic converts G3P into dihydroxyacetone phosphate, an important step that links glycerol metabolism to glycolysis. Second is the mitochondrial. It facilitates the regeneration of NAD+, which is essential for maintaining glycolytic activity in tissues like the brain and the skeletal muscle. These two forms are very crucial for the energy metabolism of the cells. Next is the alcohol dehydrogenase. This catalyzes the conversion of glycerol to D-glyceraldehyde, facilitating glycerol's entry into various metabolic pathways. ADH activity can influence metabolic balance and energy homeostasis, especially during states of hormonal imbalance or dietary changes. This enzyme is also involved not only in glycerol metabolism, but also in metabolism of alcohols and aldehydes within the body. The fourth key enzyme of glycerol metabolism is the thiokinase. It is involved in the phosphorylation of glyceraldehyde, converting it into glyceraldehyde 3-phosphate. This step is crucial because the GAP or the GAP can enter the glycolytic pathway, thus linking glyceraldehyde metabolism directly to energy production. It exhibits a high activity level in the liver tissues, particularly under caloric restriction or during fasting states when glycerol availability is increased. Next is the aldehyde dehydrogenase and aldehyde reductase. These enzymes participate in the metabolism of glyceraldehyde. Aldehyde dehydrogenase converts glyceraldehyde into D-glycerate, while aldehyde reductase can reduce glyceraldehyde back to glycerol. Aldehyde dehydrogenase has been shown to play a role in detoxification and metabolic regulation, while aldehyde reductase may assist in the interconversion between different forms of carbohydrates during metabolic stress.
And that ends our presentation. Thank you all for listening.